Hey guys, my name's Sunny, and for this video I'll be talking about my project for the remote sensing class taught by Dr. Mitchell at the University of Maryland. So for this project, our task was to design, to physically develop, and to test our own field deployable LiDAR sensor that runs on Raspberry Pi and OpenCV platforms. So we took this sensor and we went onto our Maryland campus to a specific target of interest. We collected 3D measurements of it, and processing that data, we were able to create a 3D point cloud and mesh of that target. So the target I chose is this fence by the Commons Apartments on the south side of campus. As much as I thought it'd be really cool to have an end product or model of Testudo, I wanted to choose something that wasn't as well known, yet still represented Maryland in some way. I also wanted to see exactly how well my sensor could actually map the M-shaped cutout of the fence. Originally, I wanted to map between the ends of each brick structure and everything in between, but for the sake of time, I wasn't able to map the whole thing. So for this video and for my final point cloud, we'll just be focusing on the middle structure that holds the M cutout and the brick below that. So during our course, we talked about the fundamentals of remote sensing, which is defined as the science technology of obtaining information about a target without having a sensor in direct physical contact. So under the umbrella of remote sensing, we have radar, LiDAR, and sonar. But for this project, we focused on building a LiDAR or light detection and ranging system. So this means that the source of our radiation or transmitter will be in the form of a laser light. So generally, the way that it works is that you'll have radiation, in our case light energy or photons, actively transmitted into the environment, and when it reaches the target surface, it's backscattered and detected by the receiver. And with LiDAR, you're working with shorter wavelengths compared to radio or acoustic waves, which will provide better range resolution and precision. Alright, so here's our field deployable LiDAR system. It's nothing too fancy. We have a tripod stand taped to a horizontal wooden board, which holds our transmitter, a green light from this laser pointer, and that's positioned 12 inches away from our receiver, an 8 megapixel camera. As I mentioned, we'll be taking 3D measurements of the target, which means that I need to know the location of that laser point relative to this system. So to address that, I have an accelerometer chip, and that's going to measure the static acceleration of gravity as I tilt the system back and forth like so. And so by doing this, I'm actually varying the X angle of the accelerometer chip, and that, in addition to us physically moving the system from side to side, but in fixed increments, those two measurements are going to give us that location. And so the accelerometer chip is wired to an Arduino interface, and all of these measurements will be processed by the Raspberry Pi, which is powered by an external battery and a MATLAB code provided by Dr. Mitchell. And lastly, when taking out the system to our target, we'll be using a VNC connection installed on the Pi, and that's going to allow me to see the Pi's desktop remotely from my laptop through an Ethernet cable. Alright, so now we're at the target, and I don't know if you can see it because it's dark, but there's the fence and the two brick structures. Everything's set up, and now it's time to map it. Actually, before we begin mapping, I did want to point out some key things about our target that we want to keep in mind and we want to be able to see in our 3D point cloud. The first thing is this brick structure on the bottom, and you'll notice that it sort of has a step shape towards the instrument. So the front vertical wall of the brick is actually closer to us and closer to the instrument than the surface of the M cutout. And another thing is that the top horizontal piece of the brick is actually extending further past that surface that holds the M cutout. So these are things that we want to be able to see clearly in our 3D point cloud. Secondly, there's actually a horizontal bar along the left side of the M. I'm not sure if they intentionally made it this way or accidentally left it there, but there's this thin horizontal bar that you can see in this photo that's been left and hasn't been cut out along with the rest of the M. So we're going to see if our sensor can pick that up. Thirdly, this middle component, so coming down towards the middle of the M is this piece that actually looks like someone has just pushed it or punched it back. So it's forever slanted towards the back if you're looking at the target head on. And we'll see if our sensor can pick this up as well. So this piece doesn't stand vertically with the rest of the surface around the M, but it's slightly at an angle towards the back. And lastly, I don't know if you can see this clearly, but this entire target is at a curvature, is along a curvature, so it's not completely flat. So if we were to take measurements from where we are towards the brick, and I know we're moving side to side, so from the very left to middle to right, that brick structure actually will not be at the same range from our instrument every time. So the left and the right side of it will be closer, and towards the middle you'll see that, or hopefully we'll see that the range actually gets further. One issue that I had while trying to map my target was the noise from the light behind the target. If you looked at a previous photo, there are 2 rows of lampposts behind the target, and a lot of times my camera actually confused that light with my laser. And I realized there wasn't too big of a fix that was needed. I just had to make sure that my laser pointer was on full batteries or near full batteries, because as the batteries were used up, the laser light became more dim, and it actually appeared much smaller and much more white to the camera, and so that kind of confused the camera in terms of which light it was supposed to detect and which light it was supposed to pinpoint as the laser. And so with that, I actually snipped the frame to be a little bit smaller. So in the code, you can actually adjust the frame from which the camera sees. So essentially you're adjusting the view the camera has, and you can make it smaller, more centralized on the laser light. And so I just tried to eliminate as much of the light that the camera saw, and that actually seemed to help a lot as well. So it just didn't have any light from the lamppost in its frames at times when it would have previously with the previous code. So that plus having full batteries, yeah, that seemed to do the trick, and that was really one of, or probably the only main issue that I ran into while I was at my target. Alright, so now here is the 3D point cloud that came out from the measurements that we took. And honestly, I was really happy to see this because it's pretty clear what we're mapping. You can see the M, you can see the space between the top bar and the M structure below that. You can see the brick foundation that I mentioned, the fact that there's a step shape to it. From this angle, it's hard to tell completely, but you can see from more of the points on the right that there are points that extend past the M structure, and that shows that the laser did pick up points of the horizontal part of the brick past that M component. So that looks really good. If we look at another view, as if you were looking head on to the target, you can actually see that little horizontal bar on the left that the laser did detect that. It's not completely clean, but you can tell that there are certain features that we mentioned that the laser did pick up on. I think one thing that the laser or that our instrument didn't really pick up well on is the fact that this whole target is on a slight curvature and it's not completely flat, because from what I'm seeing at least, it does look like it is flat, or that it's, you know, completely straight. And honestly, those measurements might be really minimal to be able to see in this 3D point cloud, but I would say overall it looks really good. So if we look at figure 5, it shows us all of the vertical scans compiled into one, and it gives you a side view of the target. And so from this we can see the brick foundation a lot more clearly, and you can see that there are a ton of points that show that the laser really did pick up the fact that the brick foundation does extend past the M structure. The one thing that it doesn't do so well of is show that middle portion of the M that sticks out the back, so away from the instrument. And in this figure, it would come towards the right of that vertical collection of points. And it's not very clear in any of the figures that that section does indeed stand at an angle. So let's see if our mesh shows us any different. To be honest, this is the first time that I've ever used Mesh Lab, and so I understand that what I'm about to show you is probably not the most refined mesh that you can make with the 3D model or the 3D point cloud that I have. But bear with me, I'll just show you what I have. So this is my 3D point cloud, and from this is the mesh that I was able to generate. You can see the shape, the general shape of it, of the target, and you can especially see the brick foundation, which I was really pleased to see. The one thing that I did want to point out that I thought was really cool is that if you rotate the mesh to the backside, it's with this mesh that you can actually see the slanted middle component, the part that comes down in the middle of the M. And you can see that more clearly with the surface as opposed to all of the data points in MATLAB. And so I thought that was pretty neat. I guess moving forward, if I were to have more time, I would have refined this a little more to show the M more clearly as a cutout. But yeah, this is it. Alright, so this concludes my final project. I hope you're able to enjoy watching and at least thought the project was cool. It's really new technology, or at least to me, I was really unfamiliar with how everything worked. So to be able to learn about it and to be able to build my own LiDAR system and test that, and to generate a 3D point cloud that looked like that, I was really amazed and just, yeah, had a lot of fun with it, as stressful as it was at times to figure things out. But thank you, Dr. Mitchell, for all your help and for teaching this course. Hopefully you weren't too stressed this semester to be able to teach it for plenty more students in the future. So yeah, thank you guys for watching, and I hope y'all have a nice day. Bye!